differentiability, right? And the fact that differentiability implies continuity. So if something is differentiable, if we can take the derivative, that means it's continuous. Okay. Now, we left off yesterday. We had just done, I think, example 4, and this is going to kind of, follow up with it. But the idea is trying to figure out if this function is differentiable. Now, again, in order for it has to be differentiable, it has to be continuous. So the limit from the left and the limit from the right and the point have to equal. And then in order for it to be differentiable, the derivative on both sides have to equal. Yes? Review synopsis from yesterday. So find all values of x for which the function is differentiable. Okay, basically, are there any places that it's not differentiable?
No idea. Well, there's an x, there's a 3, and there's a 0. So I mean, I'm assuming there's something there.
Something in between.
Or at least, in other words, those are the areas we need to investigate. Okay, so in my notes, I have written down check problem areas. I like the word investigate better. Kind of like yesterday, I said check problem areas. So based on what we have right here, I'm going to use the word investigate. Investigate problem areas. Okay? And so, yes, we have a problem area at 0 and a problem area at 3. So let's talk about what's happening at 0.
It's that one. Like the y value.
Okay, so are they... I'm trying to look and see how I did this on my notes. Okay. If we look at the left, and it looks like I just kind of... So if we look at the left is going to be x plus 1 squared. The right is going to be 2x plus 1. Looks like I just kind of set it up as an equation, like in other words, let's work each side and see, does at x equals 0, are these equal?
Oh my gosh. I don't have my contacts now. Sorry, that registered right here.
You've taken all day to figure this out?
Well, I remember I didn't put them in this morning because I was like, I don't want to put them in. Now I just realized it. It's a little blurry.
Interesting. Okay, so on the left,
I'm sorry.
if x is 0, what do we get?
1.
1. On the right, if x is 0, what do we get? 1. So what that's saying there,
Is it continuous?
okay, and this is where, okay. Concerned that I don't have another piece here, but okay. So continuous there. If you think about this graph, and I guess that's what I want to do here. If you think about this graph, x plus 1 squared is a parabola. Okay. 2x plus 1 is a line. Both of those pieces are going to be smooth continuous functions, yes. And they meet up. So it's continuous and it's going to be differentiable when x equals 0 for that reason. Okay?
Like,
I'm listening.
I'm trying to word this. So does that mean that this equation is differentiable because that part is?
Yes.
Okay.
Like if we're looking at, I was going to look and see, because I don't have a specific note in here, so I'm wondering if I forgot to write something. But that's, 0.24, right? Oh, Wrong file. Wrong file. There we go.
Discard solution after we choose.
Okay. So we checked continuity there. And I think I just went with it's differentiable based on what the two sides are. Based on the fact it's a parabola, it's a line, those are both smooth continuous functions. And so you've got smooth continuous functions is what is differentiable. The issues are when you have the cusp and sharp points like that, right? Okay. Now, with that in mind, I think why I didn't put it on here is, so technically the derivative on the left and the derivative on the right have to be the same as well, yes? Okay. The thing is, and this is why I think I didn't put it on there, is because you guys don't know how to find that derivative yet. And she just magically did it on here, which is why I didn't put it on, because I'm like, we don't know how to find that derivative. So I'm going along more with the general idea that a parabola and a line, and you connect those, it's still going to be that smooth continuous curve. Okay? Now, the other piece we have to worry about is at x equals 3. And I may try and sketch a graph here in a moment too that might help. What do you know at x equals 3? We need to compare
On the left equals 7.
2x plus 1. So when you put in 3 there, you're going to have 7. On the right, it's 4 minus x squared equals 1. What did we just figure out here? My graph is not even continuous at x equals 3, and so that means that if it's not continuous, it's not differentiable, right? So I'll just write a little bit of a note. So not continuous at x equals 3, and we're going to write this in intervals in a moment, but so not differentiable. Over here, this one is continuous at x equals 0. And then I'm just looking about the individual curves are smooth. And that's what I'm going to use for our rationalization right now. When we have a little bit more knowledge and we can find those derivatives just by looking at them, then that would be your proof. Okay, because the derivatives are the same, but we're just not quite there yet in terms of finding that. It says for all values of x, find all values of x for which the function is differentiable. So, where is this differentiable at? How would we write this in terms of all values? H of x is differentiable where?
What is it like when it says function is differentiable? Does that mean like one continuous thing?
Differentiable means you can take the derivative. You are able to take the derivative. Or you're able to differentiate, which is take the derivative.
Negative infinity to 3.
Negative infinity. It's differentiable through 3 or through 0, yes? So we can go all the way up to 3 with a parenthesis open. It's not including 3. Union
3 parentheses.
3 to infinity. So h of x is differentiable negative infinity to 3 and 3 to infinity. And then you can say there is a discontinuity at x equals 3. So not differentiable there. because I feel like we're a little inexperienced with piecewise. You want to graph this with me real quick?
Of course I do.
Okay. X plus 1 squared is what shape?
Grab
A
it.
parabola.
Parabola.
Move to the
Up
left.
one, down one.
Left one.
To the right, to the left.
Left one, left opposite sign.
Left one. Algebra 2.
So then does that go?
Oh,
It's
scratch
parentheses. Well, I'm just saying that this is like the big time I teach this. Yes, we went over it pre-calc, but parentheses means left or right opposite the sign.
Okay.
So thus, it's left or right 1, since it says plus 1. We're going to go left 1. That's what I was trying to get you. And this is a parabola. So we know this parabola is going to go... Now, this parabola exists when x is less than or equal to 0. So it exists over here. And where else does it exist?
Up to the y-axis.
Up to right there. Because when is x 0? At the y-axis, yes?
Yep.
So it exists to right there, so to speak. And if you think about it, this is just a basic x squared, so this would be at a height of what? 1, because basic parabola, you go over 1, up 1 to get to your first set of points. Okay. What's my next piece?
It's 2x plus 1.
2x plus 1. So 2x plus 1. What do we know about 2x plus 1?
Your y-intercept is 1.
Y-intercept is 1. Ah, so it's continuous. Yes, it's going to connect right there. And then what else do we know?
Up to
Stretch by 2.
It's a line. Think slope.
Oh, yeah.
Up to.
Wow, I can't do this, guys.
I mean, I guess it is a stretch, but just think slope. So from here up to, over 1, up to, over 1. And what do we have to go from 0 to 3? So I technically need to go up to over 1 again. Does that make sense? Because I want to go from x values of 0 to 3.
you want to open.
Yep, I just realized that. It's not what I wanted to happen. It is technically an open circle because of less than 3, yes? Then, okay, 4 minus x squared. What do you guys see there?
So it's an upside down parabola.
It is a parabola. It's not upside down. If it was upside down, you'd have the negative out front. That's what would reflect across the x-axis. We don't have that negative out front of the whole thing. We have just the negative on the x. When the negative is on the x, it reflects across the y-axis. So it's still going to be a right side up parabola. Excuse me. And in fact, usually, probably the better way for me to write this, well, it gets, I always struggle with thinking this through. Negative x plus 4 squared, but, well, that would work. That would work. Because what's that going to do with us?
Take us over 4.
It's technically going to take us
Oh, that way.
left 4, but then it's going to reflect it over here, and so it ends up at this 4. So it's a parabola based at 4, and it's from 3, 0, which means it's going to go all the way to the right and also over here above 3.
This is an interesting.
It's a piecewise function. Okay?
Should it be an open circle too?
That's close because it's greater than.
Right here it says greater than or equal to 3, which is why I closed it. It's like, I don't know, did I do it without thinking again, or... Okay. I just thought that was a good opportunity. And does that picture kind of shows differentiability there at 0, which is what I wanted it to show. Okay, moving along. Speaking of piecewise functions, hey. Piecewise functions are always challenging. Not only do the limits of the slopes need to be approaching the same value on either side of a given x value, but the function must be connected and smooth in order for the function to be differentiable at the given point. I think I just showed that pretty well. So, example 6. Find the value or values of the constant a where the function is continuous over all reals.
You set the two.
Huh?
You set the two.
In terms of,
X squared minus x equals 2.
okay. Yeah, so to set them, so yes, set them equal to each other because here's the deal. And set them equal to each other at what value?
3.
At x equals 3, right? So our big issue is at x equals 3. Now, it is ax squared minus x equaling to 2a. That's the left and the right, right? We're just trying to show, first of all, it has to be continuous. Well, this didn't even say anything about differentiability, did it? It just talked about continuous. So, right there, plug in your 3. What's happening here? Three squared is 9. 9a minus 3 equals 2a. And then subtract 9a. Negative 3 equals negative 7a, and then a is
3 sevenths.
3/7. Am I supposed to be getting 3/7? I am. I keep wanting to talk about differentiability, but they only asked about continuous here, didn't they? So, what makes this continuous across all reals for a? When a is 3/7.
I don't remember that pen classes.
Huh?
I did that whole wrong.
Ah. Okay, sorry.
It's okay.
Is that all we have to do?
Basic algebra. I literally
Well, and
can't do
that's-
basic
okay.
algebra anymore. Sorry, I swear to
And I
God.
guess, okay, and this is what I was like, it doesn't say justify, but that was the other thing I had in my notes. Okay? And that's why I was debating if I wanted to show that or not. But the key is to justify. And if we're going to justify, because again, we're just talking about continuity, what do we have to show? The limit from the left of f of x has to equal the limit from the right of f of x. And we can show this by putting a in now. Does that make sense? So we have this a value, and so that is going to be our proof. So like on the left is the ax squared minus x, except we know a to be 3/7. So 3/7 x squared minus x. On the right, it says 2a, except we know a to be 3/7. 2 times 3/7 is
6 sevenths.
6/7. So 3/7 x squared minus x equal to 6/7.
Yeah.
Except this is, I just realized, dang it. This is a limit, yes, as x approaches 3. So why do I still have x's in here?
I don't know.
I'm struggling.
You tossed 3 in there?
Yeah, we need to toss 3 in there.
Well,
Because we took the limit, yes? The
Yeah.
limit is x approaches 3. I got so tied up with putting the a in there, totally spaced the 3. Does that make sense? Sorry. Okay, so we're gonna, this was as x approaches 3, so my apologies. 3/7 times 3 squared minus 3 equals 6/7.
That's 9 times 3. 27.
Well, let's start with, what's 3 squared? 3 squared is
no.
9 times 3 is,
27.
so then you have 27/7 minus, what would it be good to think about 3 as?
21%.
That is 21/7.
That's 6 sevenths.
And does that give me a true statement?
Yes.
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 We end up with 6/7 equals 6/7. And so that is showing that that limit statement is true. And so it's continuous when A is 3/7.
Yeehaw.
Yeah, I feel like it should ask differentiability, but it didn't. And that's why I just verified here. It doesn't ask differentiability, so continuity it is.
One page down, 2 to go.
Always counting highly for my counting down.
Yes.
Okay. 7. Show algebraically, hear that? Algebraically, using alternate form of the derivative, why g of x is not differentiable at x equals 1. Okay, so it did specify alternate form of the derivative. We're trying to figure out why it's not differentiable, and our key value is x equals 1, yes? So I kind of have this written in steps in my notes, but kind of number 1, our target value that we are focused on is 1. Now, as we think about this, we're trying to prove differentiability, yes? What do we need to consider here?
You got to do the f of x minus f of a over x minus a.
Okay. In other words, we need to find the derivative, yes? And the derivative, our method to finding derivative right now is one of our limit definitions. And this specifically says alternate form. So alternate form here, you remember? I'll write it off to the side. The limit as x approaches a of f of x minus f of a over x minus a. Sound familiar? Flip back, it's, I don't know, a handful of pages back somewhere, right? But in case you needed the reminder, there it is. So, the derivative on the left has to match the derivative on the right. So, the limit as x approaches 1, you want to do left or right first?
Left.
From the left, f of x minus f of a. So keep in mind, on the left, when x approaches 1 from the left, we're going to be using x squared, correct? Just a side note there. So f of x is going to be x squared minus f of a is 1 squared if you want to get particular, over x minus a, so x minus 1, correct? Now, so essentially this is the limit as x approaches 1 from the left of x squared minus 1 over x minus 1.
For this one, would we put in like 0.9?
You could, or there's another option to get around that.
You can do the difference of squares.
Factoring.
Yes. X plus 1 x minus
Okay. Well, I'm not going to say we couldn't put in like 0.9 because that is approaching from the left. But I would see it a little easier to think of this as factoring. Because x squared minus 1 is x plus 1, x minus 1 over x minus 1s. Those cancel. Finish your limit. Hello. Yes. Okay. Thanks. Bye. She should have come down to eat lunch, though. Oh well. Okay. So, what just happened here without me? The limit as x approaches 1 from the left of x plus 1 is going to be what? 2. Yes?
Yes.
Yes.
Okay.
Yes.
Yes.
Now, the other part we need to do, the limit as x approaches 1 from the
Right.
right. Now, as x approaches 1 from the right, what do we have to remember? F of x is x this time,
X.
right? So this time, f of x minus f of a, so
X minus 1.
x minus 1 over x minus a, which is x minus 1. X minus 1 over x minus 1, it doesn't even matter if you plug anything in, does it?
0.
No, wait.
It's 1.
Cancel your factors. Cancel your factors. Officially, it's the limit as x approaches 1 of 1. So that answer is just 1. Okay? Now, show algebraically why it is not differentiable. Did I just do that?
Yes.
Yeah, I just showed that, how do I want to, let's see, what was it? It was g of x up here. The limit as x approaches 1 from the left of g prime of x does not equal the limit as x approaches 1 from the right of g prime of x. That's your algebraic part, okay? Now, graph, they gave us a graph to actually graph.
Oh, it came up.
Should be Addison. You can have a seat wherever you want. You can use your pencil, calculator, and that green paper. Okay? Okay, what do we have here, folks? G of x equals x squared. So what is that?
So algebra.
Parabola
X. That origin.
at the origin. What piece of this parabola am I graphing?
I don't know.
The left side. Left of 1.
My flowy sleeves are a problem today.
Oh, yeah.
So you're going 2, 1, and left.
I honestly don't know.
Say that again, only because I got distracted.
So you're graphing from 1 to the left.
Oh, okay, as in it goes over here, yes? So we know over here, my parabola goes up like this, yes? How far do we go to the right? We are only going up to 1, and we know it would go through the point 1, 1, yes? Okay,
That's a solid.
and it is, yep. And then x, y equals x. What is the graph y equals x?
A line.
A line that goes through
The origin.
the origin and has a slope of
1.
1.
Highly.
Y equals x, my dear. Why are you hooked on 2s? I don't. Why are you talking about 2?
The 2.
That, okay, that's our limit. That has nothing to do with graphing. We're looking at this to graph.
Oh.
Like, what are you talking
I'm
about?
following that.
Why is she so hooked on a 2? Okay, are you good now?
I think so.
She's
Yeah.
just very too.
Okay, now the point is here, guys. Okay, so it would start here at 0, but then if it's a slope of 1, it's going to go through what? 1, 1, 2, 2, 3, 3, 4, 4, so on and so forth. Yes?
There's no limit with this one.
And correct. It just goes on infinitely.
That's not a smooth.
And what's the difference between this graph and the last graph? Is this one as smooth?
Got a
It's
cusp.
it's cusp.
Yeah, and I
Sharp
can't,
point.
I didn't, it's hard for me to draw this and do this justice, but the problem is this right here. Okay, so there's your graphic support that may or may not be smooth. And by showing of the fact that our limits aren't equal, the limits of the derivatives, we know it's not smooth. Okay, so we can say graphically there is a cusp at x equals 1. Okay. Told you to bring your calculators today.
Yeah.
Did you?
Yeah.
Yes.
I just hope you
And
can
throw
throw
it
it
away.
away. Really effective.
If not, grab one from over there.
Yeah.
It's not a hard skill I'm teaching you. It's just
You need
It's
like
calculating.
calculator for this.
okay.
You said it's gonna be a trick.
I mean, it's just like last year at this time, you were just learning how to find mins and maxes on your
The
calculators.
math fun.
Now, like we learned zeros earlier on. I just taught pre-calc how to use the min and max function the other day. Okay, well, you get a new function, new function to use. So, on the AP exam, you will need to find the numeric derivative of a function at a given point. You can use inderiv is what it is on the TI-84 Plus, where she uses the TI Inspire, and that's a different thing here. So we're going to be talking about the TI-84 Plus, obviously. Now, there's a couple different ways to do it. I've always taught you Math Menu has a lot of good information, yes? Yes. Okay. So when you go into the Math Menu,
Was that?
Yes.
okay, so if I hit my Math Menu, has lots of good information. Number 8 says inderiv. Okay, number 8 is inderiv, and that is a derivative. Okay, and that's what we will be working with. Now, you can just pick Math 8. You have to enter this various information here. What this will do, this will not tell you that the derivative of x squared minus 5x plus 6 is 2x minus 5. It won't tell you that. But it will tell you is the derivative of x squared minus 5x plus 6 evaluated at -3 is -11. Okay, so it won't tell you what it is in terms of x, but it will tell you what it is if you have a value to plug into it. So it's helpful some of the time. It's not always helpful. Okay? Now, unless you have an Inspire, you can ignore this piece. Let's practice. Did you plug it in?
No.
Okay, so right here, d over dx. That's always just with respect to what variable are we taking the derivative? And we're taking the derivative with respect to x because x is what's in my problem. Then in the parentheses, you're entering your equation. So my equation being x squared minus 5x plus 6. This is the thing. At x equals, this is where you have to put in a number. Okay, you can't just leave this blank. It'll give you an error. You have to put in a number. At what number am I trying to find the derivative? -3 is what they gave us.
Oh my god.
This is
Okay.
magical.
No.
So when we do this, it's the idea that your calculator will look like d dx of x squared minus 5x plus 6. Oh, I guess that's not what I was going to write here. I guess that already shows up here, but I guess the general idea is that you're putting in the f of x is what I was showing here. And then it's, they use the bar, yeah, at x equals -3. So, know how to use the calculator to do something like this. Now, I rattled off earlier that the derivative of this function is 2x minus 5. Don't worry about the hows or whys yet. We'll get there later. That's in lesson 2.5. But the idea is that if I take the derivative and plug in -3, guess what I'm going to get?
Probably the equation.
2 times -3 is
Oh, probably the
-6 minus 5 is
-11.
-11. Okay, so that's what your calculator is doing. It's calculating the derivative and plugging the value in.
I also did the one instead of log, but the x squared after one, and it gave me 2.
What?
I did the I plugged in x squared at x equals 1, and it gave me 2.
Oh, okay. Plug in some of the others. Okay, so the calculator, again, I kind of find it weird in this book that they introduce that before we even know how to find derivatives by hand, but We'll just go with it. Okay, ready for 9? It's 9 we talk more about the calculator. I don't think it's find the derivative, but... Oh, it is. Okay. Use your calculator to find the derivative of our first 3 functions in this lesson set. Explain any problems you encounter.
Oh my god.
I should have looked back through this before we started. I'm trying to remember.
Where's the absolute value sign?
Oh, find that too.
Oh, but-
I'll find it. Thanks.
Hey, by the way, guys, in terms of shortcuts, and it's for the shortcut for absolute value, alpha F2, nope, yep, number 3 is in deriv also.
Oh, okay.
So you don't have to use the math menu, it's up there in that F2 thing. Okay, so,
What? Oh man.
Jenny?
Which one?
Jenny? It's 0. Obviously. Right?
You know, just because you said that, I hope you're wrong. You can put the absolute value inside the parentheses, right? And leave it like that. Because I can't delete the parentheses.
correct.
Okay.
Yes.
Okay.
Okay.
Yeah.
Sorry, and this I'm trying to remember how this all works on our calculators versus the Inspire versus, because notice what it said here. Explain any problems that you encounter.
Is 0 a problem?
Okay. Well, it depends on if it's the right answer or not. Okay. So think about, here's what I'm going to suggest here. Visualize with me. What do you know about this graph?
Shifted
To
to
V.
the right 1.
It'd be
It's
like
me.
this.
V, shifted right 1.
So that would be 0.
Oh.
So,
I told you.
wait. We're being asked to find the derivative
That is not.
at the absolute value of x minus 1, of the absolute value of x minus 1 at x equals 1, which is where?
Right there.
Right there, around the cusp.
Yes.
Right on that sharp point, that cusp. Okay. I would call x equals 1 a special point. Okay, it's a special point. Could we find a derivative anyplace else on this problem?
Yeah.
Sure. Except right here. Okay? And so this is kind of where I think the point of this section to her is that your calculator can't always be trusted on the special points. Okay? So something, you know, at this because it ends up being at the point. Now, if you, okay, I have written down, because she did this on the Inspire also. If you plug, so you guys were getting, what is your answer?
0.
0, yes? Which is, yes, what the TI-84 gives us. The Inspire gave her plus or minus 1. Now think about that. The slope from the right is plus 1. The slope from the left is minus 1. So it kind of makes sense that it says plus or minus 1, but can you have 2 derivatives at the same point?
No.
No. Okay, so this is one of those where, what do I want to say here? Yeah, the derivative does not exist is essentially what happens here.
Good job, Phil.
Huh.
If I kind of make an Inspire column versus a TI-84 column, just to kind of show you. Okay, here, the derivative at 1 according to the Inspire is plus or minus 1. The derivative according to our TI-84 is, derivative at 1 is equal to 0. In reality, this isn't differentiable here. Okay? So the TI-84, the comment I will make is you cannot trust this at, I'm going to use the word special points. Maybe I should say special cases. Because in reality, I'm going to say at x equals 1, it's not differentiable. Okay.
Next.
Excuse me. Okay. Try your next one. The derivative of the cube root of x at x equals 0. According to your calculator is?
Where's cube root at?
I couldn't find it either. I tried
It's
to
in
find
order.
it.
I found it.
It's also in Alpha F2, I think.
Or just go 2, then delete that number 3.
That works too.
Duh.
My first year of teaching these calculators, like I didn't know what kind of things I needed to teach you, and it was really part of the year. And I think I did, I don't know if it was a cube root or a power of 3. And they're like, how'd you do that? I would just put the 2 and have to delete it out. Like, they were so amazed. And I'm like, it's this button right here. Yes, I should have taught that. Like, now, do you guys remember what the cube root graph looks like?
No.
Was it just yesterday we talked about this?
Yeah, it's
Oh yeah, it's the
Yeah, it's the sideways one.
sideways though. It's like x cubed except it's the inverse.
Yeah, and so at x equals 0, what kind of tangent line do we end up with here?
Straight line.
one.
A vertical line,
Oh,
Yeah.
which means this is
non-existent.
not differentiable. Now, I will say, on the Inspire, it does actually come up undefined. Okay, again, this is a special case. This is one we have to recognize it's not differentiable because there's a vertical tangent line. So, I'm going to say at x equals 0, not differentiable.
I'm really excited about this. I was like, oh, this one for everything.
Well, it's kind of showing the special cases here. And I guess here I will say, you want a reason? It's a vertical tangent line. I didn't put it up above, but did you guys write it? The reason up above is it was a cusp, a hard point.
I need to figure out how to spell this. It's getting worse and worse.
What, differentiable? I always have to differentiate. I have to sound, if you see me saying something real slow, it's because in my brain, continuity is the hardest one for me to spell. I don't know why. It just is. Okay, C. Well, you find the derivative at -2.
Zero.
What do our calculators say? 0. Okay.
What does the Inspire say?
Yes.
It does another undefined.
Because it's an asymptote. Because it never actually goes through.
Did you graph it? Yep. Yeah. This, so 1 over x, okay. Work with me. Follow my brain. What's the graph of 1 over x?
It's the. Oh, it's that one.
This one, yes? No, wait.
There's that.
That's, I didn't,
Which quadrant, which way for you guys?
The other way.
Okay, so wait. I'm going to erase this here, but 1 over x is this and this, yes?
oh, okay.
Are we with me?
What's the? Well,
Now.
I think so.
I don't know. Hold on.
The,
Okay, so there's 1 over x. Now, here's the deal. When I square this is good graphing knowledge here. When I square that, what that says is instead of both pieces going opposite directions, they go the same direction. So now, scribble that out. It's that. What's the
And
plus 2
shift it
doing?
To the left.
Shifted over.
Takes your vertical asymptote to left. Did you follow that a little bit?
yeah.
Now, again, that was just me trying to get you to, Yes, you can graph it on the calculator, but I'm trying to show you that that's one, you can follow the graph in your head. So this one, guess what? At x equals -2. Shocker, I know. Not differentiable. And this time, vertical asymptote. Okay. Now, if you haven't read that bottom comment, it says, your calculator is programmed to find derivatives by using the symmetric difference quotient. This can cause errors. You must make the final decision based on proper analysis. You can usually trust the derivative button, unless you get these weird special cases. Okay? Like the derivative we did here, x squared minus 5x plus 6, that's a parabola. You can trust any single value you put in there. It's going to give back the right answer. All the ones we just gave, those are all weird special cases. Okay? If you plugged in any other value on any of these lines, you'd get a perfectly fine derivative. It's just these were picked as special cases. Okay? Okay, the bottom. Defending your answers. If you are given that y equals f of x is a differentiable function at x equals 3, explain why each statement below is true. Okay, so what is given?
Is differentiable.
Differentiable.
Which means it's also continuous.
Okay, so differentiability implies continuity. Keep that in mind. How can we defend, or how do we know that f of 3 exists?
It's continuous.
If f is differentiable, and I'm just going to abbreviate, then we know f is continuous. Well, if f is continuous, what must that say?
That f exists.
Yeah. So if f is differentiable, then f is continuous. So f of 3 must exist. Basically, by showing continuity, we know that it exists. B. The limit as x approaches 3 of f of x exists.
It's continuous.
Yeah.
Continuous. Isn't this basically what we have to show for continuity?
Yeah, it has to be.
The limit has to exist, right? For the limit to exist, the limit from the left has to equal the limit from the right to exist. So we know this is continuous. So again, starting off the same way as last time, that if f is given as differentiable, then f is continuous. Did I write anything else in my notes? If f is continuous, then the limit exists, is what I have. If f is continuous, then the limit as x approaches 3 of f of x must exist. You could also throw in there, you wouldn't have to, because it's just based on definitions here. You could throw in the limit from the left would have to equal the limit from the right.
That's just the derivative.
Yeah.
C is,
It's differentiable. Then
Yeah,
It's just the different
Okay.
form of it.
so this is our alternate form of derivative, which is good. That's why I need you guys recognizing. That's an easy one to recognize in that form, but and I don't have a ton of notes. I don't know if I wrote anything else. That's the alternate form of derivative. And what does being differentiable mean?
yeah, that's very good.
You can take the derivative, so thus the derivative exists, right? And what about that bottom one?
That's
Literally
also
the same thing.
It's the limit definition of derivative, right? So this is the limit definition of derivative.
Homework was like this.
You know the homework won't be like this,
I
though.
know.
Okay.
We can never get something.
Okay. 2.4. Work through 2.4.
Time out. Is this only 2 pages long?
It is.
What?
So
Whoa!
28
It's still
questions.
28 questions, though. Okay.
No, it's not. My pages got stuck together. It's still 4 pages.
Oh. I guess I was thinking 2 pages front and back.
No, like my pages were like this, and I was like, wait a second. No,
Okay.
they're still
Um,
same.